recording this because, yeah. Okay, so the observational units are the couples. The variable is whether they turn to the right or the left. Isabella, categorical or quantitative variable?
Categorical.
Categorical variable. Okay, that's important because that's going to determine whether we use a central limit theorem for proportions, which is for categorical, or whether we use a central limit theorem for means, which is quantitative. Okay, so that's a very important distinction here. Okay, so since describe the sample data numerically and graphically, I'm not even sure what they're talking about there. They may get a good answer for that. B. No. Kathy, get it. What did you guys write for that, or did you just draw your diagram?
I just drew the diagram.
Yeah, I think that's fine. Yeah, I think that's fine. Just draw that. Let me just see if I can get this no, wrong way. That might be a little bit better. Okay, so let's draw our diagram. First, let's kind of put what information we know. When is our n? Okay, so our n. Crystal, you here? Crystal, do you know what our n is in this problem? Okay, hang on. So I can't call Crystal twice. That doesn't work. Mila, what is our n in this problem? Do you know?
I think the n is 124.
I think so too. That's our sample size. Got 124 kissing couples. So I got 124 is my n. What is my p hat? Isabella, what's my p hat?
0.645.
How did you get it?
But I did 80 over 124.
I think that's right. So 80 divided by 124, you're telling me that equals 0.645, and that is the couples that turn their heads to the right, correct? Okay, so this is p hat is to the right, R-I-G-H-T. You guys can read the board, okay? Big enough? Okay, good. All right. So I guess we should just make our diagram, and then we're going to use that to determine a 90% confidence interval. So let's see if I can actually draw this standing up here. So not too bad. All right. So I have my, well, first of all, I need to ask a different question. Michaela, are you here, Michaela? Did you I think you got booted out. Okay, Sandra, is that okay for the shape?
Yes, because it's unimodal and symmetrical.
That's correct. It's unimodal and symmetric. But how do I know that that's okay?
I'm not quite sure.
What's the test? I want the test. What test do I need to use to determine whether I can use the central limit theorem or not?
If the n is greater than or equal to 10.
You're close. It's not whether n is greater than or equal to 10. It's n times something.
Oh, excuse me, n times pi. That's
right. Although in this case, we don't know pi. We're going to use p hat.
Okay.
Are you good with that?
Yes.
You know, we don't. Pi is the proportion for the population, and that's really what we're trying to find out. Is we're trying to get a confidence interval that says the population proportion is between this and that. Okay, but so we use p hat because we know that we can find that from our sample. So n times p hat, that would be 124 times 0.65. I mean, that's definitely greater than 10. And 1 minus 0.645 is like a third, and a third of 124 is 40. So that's definitely greater than 10. So I think I passed my test. I think it's okay to have it unimodal and symmetric. Everybody okay with that? Yes, you must do that. Okay, you must do that. So I got unimodal and symmetric, that's my shape. Angelica, what's my center gonna be?
P hat.
That's exactly right. It's gonna be 0.645. It's gonna be p hat. So remember, when we're describing a distribution, shape, center, spread, or shape, center, spread, depends if you want to go left to right or right to left. Same thing, shape, center, spread. I'm making a joke. You're supposed to laugh, it's a joke. Okay. So 1, 2, 3, -1, -2, -3, 1, 2, 3, -1, -2, -3. Now, how am I going to figure out what numbers to put here? How am I going to do that? I need to figure out what numbers to put there. So I need something to do that. So Mila, again, can you tell me how can I, what am I going to do here? How am I going to figure out what to put down here for my numbers?
So you would first, you need to find what, sorry, I'm trying to figure out the name of it. I have the actual number, but
You don't know. Tell me, how did you find the actual number? And then we'll talk, then we'll say what it's called.
I divided 80 by 124. Wait, is that right? Wait, no, that's not right. I got p hat equals 0.645.
That's right.
And then what did I do? I found the standard error, which is p hat times 1 minus p hat over n, all under the square root.
That's right. So the standard error, we need to calculate the standard error so we can know what we're going to put as 1 standard error, 2 standard errors, 3 standard errors. So I want to point something out here that is very important for the difference between categorical variables and quantitative variables. For categorical variables, we can find the standard error, and the standard error it's the same thing as a standard deviation. The only difference is that we don't know standard deviation. We would have to know what the population proportion is, and we don't know the population proportion. Standard error, we're doing it based on our statistic, but the concept is basically the same thing. We're trying to find the spread of the distribution. So with categorical variables, all I need to know is the sample size and the proportion of the statistic. If you think about what do I need for a quantitative variable, I'm just going to write it over here and then I'm going to erase it. For a quantitative variable, I need to take the standard deviation of the sample and divide that by the square root of n. So here I really only need one piece of information. I need to know the p hat, the proportion. Here I need to also know the standard deviation of the distribution of the sample. So a little bit different, but you should have that in your notes. But so if I just know the proportion and the sample size, I can find the standard error. And so Mila, give me again, what did you have for that number?
So I got 0.043 when it's rounded.
Okay, is that right, everybody? I don't know. Is that the right number? That's right. I'm getting yeses. Okay, great. All right. So then, Emily, do me a favor and read me off the numbers here for 1, 2, and 3.
For 1, I got 0.688. For 2, I got 0.731. And for 3, I got 0.774.
What about going the other way?
For -1, 0.602. For -2, 0.559. And then 0.516.
Okay, so is that looking good to everybody? We're looking pretty good? Okay, now, well, okay, so, okay, we described it there. I need to determine a 90% confidence interval. But before I do that, I just want to point one thing out again that can get confusing when you make this diagram here for proportions. And what gets a little bit confusing is that all the numbers on the bottom here for proportions are going to be between 0 and 1. Okay, they're all going to be a decimal between 0 and 1. And where that can kind of throw people off a little bit is if you end up having to use normal CDF to find the area under a portion of the curve. We know that normal CDF goes from a Z on the left to a Z on the right. And these proportions look deceptively like a Z-score. They are not Z-scores, they are proportions. You have to remember you need to calculate the Z-score to put in normal CDF if that's what you're going to need. Do you follow what I'm saying here? Right? If I was dealing with something like weight, right? Then these numbers down here, 160, 165, 170, they're bigger numbers and they don't even work as Z-scores. So if you tried to plug those in, you'd get an error. But with proportions, if you plug in the actual number instead of a Z-score, you're going to get an answer. It's just going to be the wrong answer. You follow what I'm saying here? So you got to be careful to make sure that if you're going to use normal CDF, you're going to put in Z-scores. So let's erase that. Come on, stay still. Okay. Did that show up as green? Could you see that was green? Can you see the colors? Yeah. Okay. I'm not sure because on mine it all looks blue. Okay. So I need to find a 90% confidence interval. I know that between 1 and -1 and 1 is 68%. And I know between -2 and 2 is approximately 95%. So what that tells me is that my 90% confidence interval is going to be somewhere in here, between 1 standard deviation and 2 standard deviations away from the mean. This is going to be my 90% confidence interval. Bigger than a 68% confidence interval, which would be from 1 to 1. Smaller than a 95% confidence interval, which would be -2 to 2. So I know it kind of goes in there somewhere, and that enables me to make my diagram a little bit better. So I know that this is 90%. Does that make sense to everybody? We're good? We're still going okay? Any questions? Stop me if I have questions. No, stop me if you have questions. I don't have any questions right now. I'm doing okay. Still good.
Could you actually explain that one more time?
Yeah, okay. How I got that 90% was between -2 and 1 and 1 and 2?
Yes.
Okay. So do you remember the empirical rule, Angelica, that says between -1 and 1 is 68%, between -2 and +2 is 95%, and -3 and +3 is 99.7%? Okay, so I'm only looking for 90% confidence interval. Well, if this between -1 and 1 is 68, and between -2 and +2 is 95, then I know that 90% has to be somewhere between -1 and 2 and +1 and 2.
Okay, got it.
Are you sure?
Yes.
Okay, all right, great. So 90%. And 90%, since it is symmetric, means it's 45% on that side and 45% on that side. So from here to the line that I want, and this is what I'm looking for. I'm looking for this line right here is 45%. So if I go from 0 to the middle, I know that's 50% because the middle is by definition 50%. Yes, we're good. Okay. And then from here to where I want to be is 45%. So I know that this line right here is at the 95th percentile. Are we good with that? Everybody good with that? Okay, now I'm just gonna, is that a thumbs up, Susie, or was that a hand up? Thumbs up, got it, okay, good, all right. So, what I'm looking for in this is a confidence interval. And the confidence interval is gonna look like an interval, like interval notation, and it's gonna have, a comma there. And it's going to have a number on the left and a number on the right. And this number here is going to be somewhere between 0.559 and 0.602. And this number here is going to be somewhere between 0.688 and 0.731. Now, I know that because when we were doing it before, my 90% confidence interval are like these red lines here. But a confidence interval is saying, I want a couple of numbers between which I am 90% sure the actual population parameter lies. I'm going to say that one more time. I'm looking for some actual numbers, some actual proportions between which I know with 90% confidence that the actual population parameter lies. Does that make sense what I said to everybody right there? That's a very long sentence, a lot of clauses, okay? We're okay with that. Okay, great. So I'm trying to find, when I want to find my confidence interval, I want to find this number here on the right. I want to find the one that is to the right of the mean because that's the easiest one to find. And that's the one that's because that's the easiest one to find. So I know it's a 95th percentile, but that doesn't give me the number. I cannot go into normal CDF with a percentile. I have to go in there. I'm trying to find a number. So magic bulb, here we go. A hard question. Sandra, I know the 95th percentile. How am I going to find the number between 0.688 and 0.731 that corresponds to the 95th percentile? How am I going to do that?
Using inverse norm.
I'm going to use inverse norm. So inverse norm, the argument of the inverse norm is a percentile, right? So my percentile is 0.95. So that gives me, I got to pull up my calculator here. Oh, you can't see the calculator anyway, so I can use my blue calculator. Okay. So I can go inverse norm. Nope, clear that. Okay. Inverse norm 0.95 because it's the 95th percentile. I get 0.164. Does that sound okay? Did you get that? 0.164? Okay, good. So I got, what was that? Not 0.164, 1.64. That's better. Okay. 1.64. So that is the z-score for this spot right here, 1.64. But that number isn't between 0.688 and 0.731. I need to find the number. So I got the z-score. How am I going to find the actual number based on the z-score? Michaela, can you help me? Oh, wait, Michaela, you back? Yeah, you're back. You came back on. Can you help me with that? Okay. magic bowl was paltry. Mila again. Can you help me? How am I going to find the number if I know the z-score?
So if you know the z-score, and you're going to be solving for x. So x equals p hat plus or minus the z-score times the standard error.
Very good. Okay, so I'm solving for x, p hat plus or minus the z-score times the standard error. So I know what p hat is. P hat is 0.645. So 0.645. I'm going to do plus first, and then the z-score is 1.64 times my standard error, which is 0.043. So for this number over here, I'm going to get 0.645 plus 1.64 times 0.043. I get 0.7155. 0.7155. So that is between 0.688 and 0.731. Yes? Good. And then I want to go the other way. I get 0.5745. 0.5745, because I'm just doing minus. So my confidence interval is 0.5745 to 0.7155. Is that a number you already got? Yes? Okay, so what I want somebody to tell me is in words, what's that mean? I know you can find the numbers, but what does that mean in words? Susie, what does it mean in words? What does that mean in words? I got these numbers, so what? What does it mean in words?
This is like a guess, but so like if you were to so you have n, which is 124. If you were to record that, there'd be between the intervals, that would be how much the likelihood of 95%, 90% of the couples to lean right.
You're getting very close. You're getting very close. Okay, that's good. What this is saying is that I am 90% sure that I'm 90% confident that the actual population parameter of all kissing couples, somewhere between 57.45% and 71.55% turn their heads to the right. Should I say? I'll say that again. I am 90% confident that in the entire population of the world, because this was taken from 3 different countries in many different parts of the world, maybe I could just say those 3 countries. Forget that. Okay. For the entire population of kissing couples, the proportion that turn their head to the right is between 0.5745 and 0.7155. I'm 90% confident of that. Am I 100% confident? No, I'm not 100% confident. Is it possible that the proportion of people that turn their heads to the right is like less than 50%? It's possible. I'd say it's pretty unlikely, but it's possible. But I'm 90% sure that it's between these two numbers. Are we good with that? Okay, I will ask you on a test to write that out in words, right? So be aware that you're going to have to know what this actually means. In addition to calculating it, you got to know what it's talking about. Okay, any questions so far? Okay, margin of error. Margin of error is really pretty straightforward. this right here is my margin of error. Really, if I just take the z-score and multiply it by the standard error, so let's do that. The z-score is 1.64 times 0.043. I get my margin of error is 0.0705. So margin of error, M of E, is equal to 0.0705, 0.0705. Well, let's think about that for just a second. This was my p hat. This is right in the middle. If I go 0.645 and I add 0.0705, well, I get 0.7155. And if I subtract it, if I subtract my margin of error from 0.645, I'm going to get 0.5745. So the margin of error is just taking, this is the interval for the whole thing. It's taking that, dividing it by 2, and it's saying, really, it's just saying, hey, you know, I think it's 0.645. So I could say the population parameter is 0.645 with a margin of error of 0.0705. It's saying the same thing as the confidence interval, it's just saying it in a different way. It's saying that the population proportion, I'm 90% sure that the population proportion is 0.645, but there's a margin of error. I could be wrong by, say, you know, plus 0.0705 or minus 0.0705. That's my margin of error. Does that concept make sense? Is there a question about it? You sure? Okay, I'm counting on you to tell me. All right, so we got margin of error, all right, and then E says, oh, based on these intervals, whether or not it's plausible that 50% of all kissing couples lean to the right, 2/3, 3/4, okay. So 90% confidence interval. 90%, that's pretty good. I mean, you know, you get a 90% on a test, that's an A, right? Well, an A minus, right? But I mean, 90%, that's no joke if you're 90% sure of something. I mean, if I was 90% sure of something and I was going into a casino and I was 90% sure, I'd be betting the house, man. I'd take my whole life savings and put it down over and over again. You know, 90%, yeah, I mean, you know, that's a lot of confidence, 90%. So if somebody says, well, that's all great, Mr. Jenkin, but you know, I think that really the proportion of people that kiss turning their heads to the right and the people that turn their heads to the left, I think it's even. I think it's 50%. You know, and is that plausible? I'd say, well, you know, you could be right, but really, I don't think that's really very plausible because 50%, that's like way over here someplace. That's way out of my 90% confidence interval. I mean, that's even beyond my margin of error. That's way beyond my margin of error. Well, no, it's about one margin of error. So no, I do not think that's plausible. No. Does that make sense, Emily? Because you guys said you guys struggle with that problem. Yes?
Yeah, that makes sense.
Okay, and so the other one is, well, what about 75%? Somebody says, well, so many people are right-handed, they must kiss turning their heads to the right too if they're right-handed. And you know, I don't think that. I mean, I don't know. I think how many lefties do we have in this group? We have any left-handed people in this group? Not a single one. Even you people with your cameras off, nobody's left-handed. Wow. Okay. So somebody says, I think since so many people are right-handed, more than 71% are going to turn their heads to the right. And I think it's 75%. I think it's 3/4. And I'm going to come back and say, well, you know, you can go ahead and believe what you want to believe, but the fact is that I'm 90% sure that 75% is like way out here. That's not going to fly with me. I don't think so. But somebody says 2/3, that's 67%, 0.67. Now that's within my 90% confidence interval. I'd say 0.67. Yeah, I mean, you know, that's pretty reasonable because it's within my 90% confidence interval. Does that make sense? Are we okay with this? Everybody? Yeah? Okay. Did my wife just come home? My wife just came home. Now I got to tell you something. So let me get out of this big head mode here. 3 and that's better. Okay, so yeah, I told you guys that I'm teaching remotely the rest of the year, right? And it's because of my age and my wife's age, and my wife has this immune system issue, right? But yesterday, she went to the supermarket for the first time. First time in a year. And now she just came back. She went to Trader Joe's. I mean, like, this is like mind-boggling, you know. So we're actually getting some groceries. All right. The technical conditions, part F, we finished. So I think we are, I think we have finished this section. Does that sound okay? Okay. So let's just take a quick peek at the next section. We're not going to do it a lot here. No, let me just see actually if there's anything else I need to discuss. I don't think so. No. Okay. So hang on a second here. Topic 17, test of significance. Okay, let's open that up and let's get you guys back up here. Okay, so you don't have to take any notes on this. I just want to give you, really what I want to do is I want to give you enough information to be able to have nice dreams over the weekend, you know, about statistics, right? So test of significance, it's same old, right? Normal model, what percentages go here and there. I mean, it's really going to be doing the exact same thing, but we're going to use some additional terminology. Let's see, do I have the, yeah, these are the key terms that we're going to end up using. So this will give you a lot to think about. We're going to talk about, we've mentioned statistical significance in the past, but in kind of a general way. But now we're going to have something very specific that we're going to define as something is statistically significant. And we're going to learn these new terms called the null hypothesis, the alternative hypothesis, and one-sided and two-sided. We're going to learn about test statistics, and we're going to learn about this thing called a p-value. Have you ever heard this word p-value before? Okay, well, okay, somebody guess what the letter P stands for in this. Come on, somebody guess. Oh, come on, you all know what it is. When I tell you, you're going to be, oh, I should have known that. Any volunteer? A volunteer? Kaylee, you going to volunteer?
Proportion?
Oh, that's very close, but not quite. That was a good guess, though. Good. Probability. It's probability. What's my probability value? That's what we're trying to find out here, right? So these are some terms that we're gonna learn about, and yeah, I think we'll just stop there. Yeah, let me end the recording.